somebody just go straight through a red.
Oh my gosh.
Like, and they were like eating food and stuff. Like it was obviously they just weren't paying attention.
I had someone do that to me like a week ago, and I thought it was going to be mine. I mean, I've only been in one bad accident, and that was like when I was 17 and I wasn't driving. But this guy blew this stop sign, and it was a kind of a merging thing. Like I saw him coming, but there's a stop sign there, right? So I'm just assuming he's gonna stop. Just blew it, like, and I was coming, and like there's a barrier, like I don't know how we didn't come together in a big way, but we didn't. Then the guy behind me blows his horn because I threw the anchor out. Like, dude, not just see that? It's so funny. All right, this is what we got left. 2 lectures, the 5th and the 7th, and then a final on the 12th. So that'll be at 8 o'clock. Open book, open notes, probably be 4 or 5 problems, and they are going to be out of each chapter, but we will talk about it more on Wednesday. Okay, there'll be the big concepts out of each chapter. That's the plan. I have the grading updated, so everybody needs to go in and look at the grading when you get a moment. If there's a 0 somewhere and you want to do that assignment, you can turn it in, get some late points. Okay. But make sure you go through it and look at it. There are some 0s in there that didn't make sense to me, but I graded everything I have and I went through all the emails. So I'm going to put it on you to go look when you get a moment and communicate with me. All right. Questions on that? Everyone's good with that? Everyone's good with Monday? No problem. 8 o'clock. All right. Yeah, the final schedules has us at 8. So I think final schedule will get away from these weird start times and just go, which is odd, but I don't know how else they could do it. But yeah, we're 8 to 10:50, I think. No, 8 to 9:50. It's 2 hours. All right. We are going to move into, that's weird, doesn't show it. Oh yeah, it does. Open channel flow. So today's going to be just about definitions. I think we'll define 4 or 5 things about open channel flow, and then we'll work our way to what's called critical depth and some flow rates. So this is not my area of expertise. I'm going to hack my way through it. This is very civil engineering, but it's also fairly interesting and not too difficult in the beginning. So what we're looking at is these kind of systems that transport water long distances over very low grades. So they're called channels or weirs. Oh, wow, lights are out. They can be concrete channels, right? They can be natural type streams. We did a little bit of that already. Not very often that they're full culverts, but I think they do exist out there somewhere. They can be concrete or earth. You see them all different ways. The things that we have to define so we can move towards flow rate is this information and this information. So we all know what a cross section is. That's chopping the channel to give us a cross-sectional view, right? So we'll need both of those. We'll need this side view and some information. And we'll need the cross-section to get things like wetted perimeter. So our goal is not just the depth, but what's called the critical depth. So if you think about this thing, it's not a stagnant piece of water, right? It's moving. So we have friction involved in the sides and the bottom that's actually holding the water back. And then we have a slope that's trying to get the water to flow. So water's going to sit horizontal, pretty close to horizontal in a channel, right? It doesn't sit parallel to the bottom of the channel. It sits horizontal and then it flows, which is really strange because there's, just portions of it that are horizontal. You can kind of see how it moves down with some rippling effect, but it's really trying to find it's horizontal, right? It's trying to find level. So we need to know things like the slope of the bottom, that's S sub O. We need to know the surface of the water and the depth at a cross section. So when we talk depth, it's at a cross section, right? And when we slice it, we look at it from this angle, we see the depth. There's a couple depths that we're going to work with. There's the regular depth that could be given, and then there's what's called a critical depth. But that'll be on Wednesday when we calculate those. Then there's this thing called the energy grade line. The energy grade line is parallel to the bottom surface. So it's parallel to the slope. Okay. And then the energy, the kinetic energy due to the moving water is this distance right here, the difference between the energy grade line and the bottom surface. Okay, so obviously the energy grade line is not a real thing. We can't see it, right? But we can actually calculate the EGL, energy grade line. There's also something called a hydraulic grade line, which we may calculate if we get that far. All right, so this is how it sets up. What we need to do is we need to be able to calculate a few things just based on information given to us, like the slope. Slope's pretty simple, right? Everyone knows what slope is. Anyone know what slope is? So I'm going to call it S sub O. Yep. Say again. Yeah, rise over run. That's exactly right. So the term that they're going to use is vertical fall. So that is the rise. So if we have, oh, yeah, sorry, I need it up there though, because I'm going to be here. Focus. There we go. Right, so that's the vertical component, rise and run. This is normally run. So they're calling it vertical fall over horizontal run. Right? So if we have like 300 feet of weir or channel, right? We're going to transport water 300 feet and we have a fall of 4 feet. We would get this slope. So what's that give us? 300 divided by 4. Oh, I got it the other way around, don't I? Yeah. 4 feet. Sorry. Vertical falls on top. And 300 feet. I'm like, wow, 75. That's a big number. Right? We should be pretty small. Less than 1. So what's that? 0.0133. Right? And the units are none, unitless, because we have feet divided by feet. So that's the slope, but we also often give the slope in percent, right? So if we just multiply by 100, we get 1.33% slope. That's a pretty common ratio. 100 to 1, 300 to 4, all of those kind of ratios are going to work well with open channel flow. If you get it going too fast, if you have too much slope, then your water is going to turn turbulent and you'll get a number of problems from that. You'll get your weirs, if they're natural weirs, you'll get some eroding in those channels. If they're concrete, not so much, but we don't typically want a turbulent flow. It's just less efficient. Much less efficient. All right, so the other thing we need to be able to calculate is wetted perimeter. So if I have a channel that is rectangular, let's say it's 5 feet deep and the water is 3 feet and we're 6 feet here. The wetted perimeter is just what it sounds like. It's the wetted area of the channel. So we're going to use wetted perimeter. We're going to use slope. we're going to use hydraulic radius, all of these things that we want to define and be able to calculate. Once we have that and some friction factors, we can come up with the flow rate of these channels. So wetted perimeter of this, and I just say wetted perimeter with a WP. I'm not sure what they use for wetted perimeter. Just P, looks like. How much? 3 feet plus 6 feet plus 3 feet, right? Yeah. 12 feet. A little more challenging if you get a channel that looks like this. Then we need some length of arc calculation. So you might have to look that up. I think they have some arc length calculations in the book, or even a trapezoid, right? And this usually is water surface. A little triangle. So this can become more difficult if it's just not rectangular. If it's one of these other shapes, we still need to be able to calculate the wetted perimeter. Next is hydraulic radius. I use HR. What do they use? They use just R. And the hydraulic radius is the area divided by the wetted perimeter. Again, these numbers are going to combine so we can calculate a critical depth. And from a critical depth, then we can calculate a flow rate. So if we don't know this depth, D, right, then we can't get a number of things. We can't get wetted perimeter if we don't know the depth. We can't get the hydraulic radius if we don't know the depth, right? So if the depth is given in the problem, that's a simple problem. You just can calculate a lot of stuff and go for it. But if we don't know the depth, like if we're doing design work and we know kind of the slope and we know how far we want to travel the water, that could give us the slope, but doesn't give us the depth. If we know how much Q we want flow rate, but we don't know channel size, right? We have to work it from a lot of different angles. So if we look at this one, we should be able to get the hydraulic radius. So A is area divided by wetted perimeter. So the area of this one is 6 times 3, right? And those are feet. And then the wetted perimeter is 12 feet. $18 divided by 12. 1.5. And what's the units of that? Yep. Which makes sense with, right? It is called a hydraulic radius. I don't know if you all remember radius of gyration, same kind of thing. Radius of gyration was in strength of materials, had to do with the cross-section area of a beam. Hydraulic radius, similar thing, has to do with the cross-sectional area of a channel. Says a hydraulic radius is not truly a radius in a geometric sense, but merely a term defined to give an indication of hydraulic efficiency of a channel. There you go. So weird when that light goes out. So in the book, they talk about types of channels. This is actually a pretty good chapter to do some reading because the next stuff after this stuff, so we just did kind of this beginning stuff and your homework's going to be on that. Then we're going to go into critical depth, right? And try to understand this critical velocity from our critical depth. And this diagram with, here's your depth of your channel. Your critical depth is like this convergence between this energy grade line and this E to D line. So we have to be able to kind of graph the channel to come up with those numbers. So once we go through critical depth, then we'll move into this calculation where we have a Q finally. We have the top width of the channel, that's this T. We're going to get our flow rate, cross-sectional area, and then gravity, right? So the problem with the top width of the channel is we would need to know what? To get the top width of the channel, we need to know the depth. So everything is kind of driven off this depth thing. If it's given, like if we can just go out and measure it, then we can come up with Q right away. If it's not given, then we have to calculate it. And that's going to be this equation. So we'd need Q, right? So it's kind of a game of these equations and what we know and what we don't know and kind of choosing the correct equation. All right, let's do just a simple homework problem. These first ones are going to be pretty simple. We can work number one together and then we'll move on, call it. So number one says a surveyor goes out, finds the bottom of a rectangle channel drops 3.75 feet. So we have a rectangular channel. So there's a cross section and then it drops 3.75 feet, distance of 200 feet, right? And they want to know the slope. So find the slope in percent. That one's pretty easy. What do you get? Yep. %1.88%. Yeah, then they just go on with the channel calcs. Like, you know, find the wetted perimeter of this. Pretty simple. You have to do some, you'd have to know these angles out here. 3 feet, 1 feet. Yeah, we should be able to calculate that. So like on number 6, we want a wetted perimeter. Remember, it's these lengths. So you're not going to always be given that, right? This you'd have to trig out knowing that this is 3 and this is 1.5. And then the area of the flow. So once you have all that, you could calculate the area. They have an example problem. They just go into all the trials. Yeah, they don't do any simpler ones. Yeah, let's wait to do those. So their example problems, their first one's pretty simple. That's this one. Essentially what we're just doing. And then the next example problem, they go into their trials. So this one says, find the critical depth in the trapezoid channel, having the bottom width of 6 feet and a 2-to-1 side slope. The channel's lined with concrete, good condition, carries 80 CFS. So that's important. If we're given 80 CFS, that's the Q in this equation, right? So we should be able to come up with a top. Did they give us more than that? No, they want the critical depth first. So since we don't know the depth, right? We don't know D. They go through this trial. 1, let DC equal 1 foot. Then they run equations. Okay, so this would be really good for you to try to work your way through using these equations. Like your homework's going to be pretty simple. You're just going to calculate slope, wetted perimeter, area, right, of different channels in preparation. But what I'd also like you to do is work through this example problem 6.2 and try to figure out like how they're doing this. Well, what they do is you really need a critical depth. You really need a critical depth to run those equations on the previous page. If you don't have it, you can't do it, right? So they're gonna have some target numbers when they put in their critical depth of 1 foot as a trial. Then they can calculate some things, right? They can calculate this area divided by T at 51.2. It says this value is then compared to the value of 199 already computed for Q squared over G. So they took their Q and they divided it by G. They square it and divide it. So that equation is essentially this equation here. So anyway, it's pretty tricky how they do this. But they ended up with this 199 as the target, right? And they got 51.2. So it says, oh, choose a higher value. So then they went to 2 for the critical depth. For their second trial. And again, they run these numbers, right? And T gives us 14 feet. So then they run through again, and now they're at 571. 571 is greater than 199. So the correct value of DC lies between 1 and 2. So it is this kind of trial system where you start with a critical depth of 1, then they did a critical depth of 2, and now the number is greater than the 199. You'll see where they get the 199. It's this A3 divided by T, right? So then they can go to trial 3 and they use this 128, and they did that through interpolation. So if you've not done interpolation before, it's how you determine a good guess between two numbers based on information, right? So the 199 minus the 51, the 571 minus the 51, and then you can solve this down to a decent guess. So I would say spend some time on this one, and then we'll do some problems like this. And I think you'll kind of get the flow of it. But in the end, they come down to an estimate for the critical depth. And from the critical depth, then you can get like channel dimensions and water flow. So it's a long example problem, but if you understand the first trial, then you can just make more trials. I think they go through a second interpolation. No, they don't. But they did kind of table it out, right? In the end, trial 1, and then all the numbers, trial 2, then all the numbers, trial 3, 128, then the numbers, trial 4, 1.5, 1.49, gives you 200. Remember, the target number there was 199, so that's pretty close. 205 I thought was pretty close. So, all right. So your homework is not that yet, but that's what we'll do on Wednesday. We'll try to grind through a couple of them in class. I think you're going to do 2, 3, 4, and 13. Yeah, 13. So on 13, so the diagrams are below. It's kind of strange, but diagrams are below the number. So this is our diagram for 13. And it says refer to the channel cross section, determine the channel dimensions by scale. So here's the scale. 1 inch equals 50 feet. So you'll have to figure that out. Like, hopefully you have a ruler of some kind. Even a measuring tape will work. 1 inch equals 50 feet. So from here to here, that's 50 feet. And then the vertical, 1 inch equals 5 feet. That's weird. That's weird. So good luck with that. But then we just want the normal depth, and the normal depth is the greatest depth, just so you know, DC. And what is the cross-sectional area of the flow? That you'll have to calculate. AutoCAD would be sweet for this, just saying. Yeah, what is the wetted perimeter? That's all the wetted area. And what is the hydraulic radius? So 13 will take you a bit. Questions? It's pretty simple until you get to that example problem 6.2. So it's going to help us Wednesday if you go through that as much as you can. All right. Yeah. Yeah, there's a pile here. Yeah, the gutter lab, how'd that go? How'd the gutter hold up under the
gutter work? I don't think the downspout.
The gutter 100% does not work in the 100-year storm. Absolutely not. Not designed for it. So that puppy overflows. And then of course, if the gutter doesn't work, then the downspout definitely doesn't work. But over here, my gutters are so clean right now. And when we get that thunderstorm, they just overflow like crazy. So they're not designed for it. I think the mesh covers are great if you don't have a whole bunch of material coming down. Like I have maple trees around, and maple trees have this ability to stick to anything. And then I have a metal roof, which doesn't help. So they just stick on my roof and then slide down. I have those. I don't have the expensive screens. I have the cheaper ones that you just clip onto your gutters. Yeah. I have them on the high. I have a very high side to my house that I'm not getting up there to clean those gutters. And, you know, in average rain, they work fine. But in the fall, when everything falls on them, they don't work for a while until everything gets washed off. So you don't want the plastic ones, I'll tell you that, because the plastic ones over time just curl up. Yeah, and then it just catches everything. It's like, yeah, the aluminum ones are better. Yeah, much better.
They're more popular now, but I've heard that they can make it paint and clean, like the stuff that gets the wood.
Oh yeah, they do for sure. Yeah. No, there's lots of good design opportunities for you in gutters because there's no good solution right now out there still. Leaf guard's great, but if it rains hard at all, it just misses. Like the water just literally misses the gutter. Because leaf guard, you know, works like a, I don't know if you know, I thought it was an interesting design. So here's a normal, how am I going to draw this? Here's a normal gutter.
think on mine, there's like a lip and they'd slide into like.
Yeah, so leaf guard literally has a area above and then a curl like that. So the water comes down, wicks and goes into the gutter, and then a leaf would come down and go around. That's the theory of the leaf guard. Well, if it rains hard, that's what the water does. It just shoots it right past the gutter. So, I mean, your gutters the gutters do not clog with
Why
the
don't you
leaf
put
guard.
like holes in it then? Like,
The holes would just fill up with crap. I think they do have some holes in them, but not much. Yeah, the whole system is this wicking. The water comes and wicks around into the gutter. And in an average rain, it works pretty good. Any kind of hard rain and it just shoots right past it. Like sprays right up the roof.
How's that not like a violation of some kind of code? Because you said they
I
require.
think,
you to have a
yeah,
catch.
no, I think they get a certain percentage and that's all they hope for.
Cause it wouldn't make any sense if they require you to have like a catchment now.
I don't
if it just
know.
Runs off.
Honestly, I don't know if there's any code to the gutter itself. There's code to the downspout. But the gutter itself, I don't,
you can slap any gutter.
I mean, you see gutters all the time. They're just falling off houses like. Probably not new houses, so maybe you couldn't get away with that.
There's some like old stuff.
Yeah,
You can't really regulate the super old stuff and just force everybody to get. new
No.
gutters.
absolutely not.
'Cause we
But
have
honestly, I don't know if there's
sense.
any. I don't know of any code to that. Maybe the gutter guy does, because I always just call a gutter guy, you know, do my projects. All right. That's it. Stay warm. See you Wednesday. We will wrap it up.
I will send you that.